Hi, check out what I scored on eBay for just over $100. A classic Fluke 45 dual display multimeter. I used to lust after this thing. Saw it in the magazines back in the day. We're talking 1989 here. Okay, this is before the internet. The only place you saw this advertised was in the magazines, of course. The electronics magazines that have the full page ad in there. And I so wanted one of these babies. Why? Because it was, I believe, the world's first dual display multimeter. You take that for granted these days, but check it out. Let's power it on. And by the way, this thing was bought like sold as is. So there was, it wasn't shown working, just, sold as is. That's it. So I thought, hey, maybe it'll be a repair video and stuff like that. Well, let's power it up and see. Ta-da! Look, dual display, dual display. Oh, I can see a bit of flicker. Can see a bit of flicker on the display. Trust me, that's not the meter. That is the just the refresh rate of the camera, so it's not actually too bad. Now, this thing, yes, it had the beautiful second display on the thing. Sadly, this one, the vacuum fluorescent display on here is quite dim, so yeah, it's not the best. That's not just the video here. It's it's pretty dim in real life as well. And you could call up the second display here, and look what else it had, which was nope, that's the baud rate. It's that M there actually means middle update rate, but it actually had different update rates. Look at this, fast update rate. It'd actually have 20 times per second fast update rate in 3000 count mode. So in, as a basic 3000 count, 3.5 digit multimeter, 20 times per second updating. That was brilliant for the day. And then you could whack it in slow mode. That's what the S there stands for. And it'd give you 100,000 count. So it was better than 4.5 digits. Back in the day, 4.5 digits meant, 20,000 count. This thing would go up to 100,000 count, and you can see that we actually got the extra digit there. Or in medium mode, it'll do 5 times per second. Oh, by the way, yeah, that slow one, 2.5 times per second updating. So back in the day, this thing was the duck's guts, the bee's knees, dual display. You could display, say, DC and the AC ripple superimposed on that at the same time. I know that's, that's nothing these days, but back then, that was a big deal. And look, it's also got a recent cow sticker on it, June 2013. This is what made me dubious about the ad. Dubious in that I wanted a meter that I could actually do a repair video on. And as you can see, it seems to be like, basically operational. Whether or not it's in cow, I don't know. I've got to get my cow meter out and check it. But yeah, it had a recent cow sticker on it. Yeah, the plastic is yellow due to the bromide. But yeah, I think they just didn't really have the ability to test it. And sometimes you can genuinely get that. So yeah, I mean, not the world's best condition. That yellow makes it look a bit yucky. The vacuum fluorescent display is a bit dim, but apart from that, she's all right. And it looks like it came from a company called PowerWave Technologies, whoever they are. And if you're looking to buy one of these, yes, you can use it anywhere in the world. Universal AC main supply input, GPIB, and this one had a very nice isolated RS2, I believe it was isolated from memory, RS232 out that could, I believe, give you like a standard string output formatting. So yeah, terrific. And made in the United States of America by John Fluke Manufacturing Co. Incorporated. Beauty. Let's take a look at the data sheet for this puppy. This was really advanced for 1989. Let me tell you, as I said, that fantastic dual display, which really set it apart. True RMS, of course, standard with the, the GPIB was optional, but the RS232 standard. It could do frequency measurements up to 1 megahertz, kind of a big deal back in the day. As with all multimeters, they had, dB measurements was a big thing for, and selectable low reference level as well. So, for audio measurements, I mean, that's pretty much gone the way of the Dodo. It doesn't matter if your meter had, audio dB measurement capability with references nowadays, but back then, yeah, that was a big deal. A big thing back then, it had a high-low intolerance test for automated production testing and that, so you could program in your specified value and then you test your product under test on the production line. It'd tell you whether or not it's within spec, pass or fail. Fantastic. 0.05% DC accuracy for current loop stuff. It's got the famous Fluke touch hold. We'll test out the audio continuity, and yes, it had an optional rechargeable battery. I don't know if this one has the battery inside. I have no idea. We'll do a teardown of this. And it had closed case calibration. You could actually calibrate it through the RS-232 port. That was a big deal for the time. And there you go. There's the different count modes with the different updating. Very nice feature. Check it out, this puppy can hold its own today. We're talking about 0.025% plus 2 counts on all the ranges from 300 millivolts up to 1,000 volts. None of this, you know, different on the millivolt range or anything like that. Absolutely fantastic. That's the 1 year nominal accuracy. The AC range, it could go up to 100 kilohertz, so it could definitely do the audio frequency range, 5%. 0.2 is pretty good for a true RMS accuracy meter back in the day, so that's awesome. The continuity tester, decent compliance voltage, 3.2 volts, so you could probably test, you know, you'd be able to test a white lead with that these days. 0.7 milliamps and 0.05% plus 2 or 3 counts, right up to 30 meg over the full range. That's kicking ass on the ohms capability. Fantastic. And current is very impressive as well for a meter of the day. 0.05% on, sadly, it didn't have a microamp range, though. It only had a milliamp range, but geez, you know, pretty impressive specs, though, for current. Most meters don't do current all that well. This one's, quite reasonable. And burden voltage, fairly typical. And as I said, dual display, we could just hit second there, and we can go AC function like that, and then put the AC in the second window there, or we can actually do current. I can't remember if it actually does current and voltage at the same time, but oh no! I think the EEVblog curse has struck again. It works! Oh, what a bummer! I was hoping to get a repair video out of this thing. Oh, well, hang on. Let's try 100 millivolts. Look, that's practically bang on. That's practically bang on. 10 volts. Oh, damn it. Arrgh. There we go. I've put it in 100,000 count mode. It can't actually go to 100,000. It can only go to 99,999. So I've selected 999 there, and there it's bang on. Like, I haven't even let this thing warm up properly or anything, so you know, that's it's pretty much bang on. And if we go to current here, damn it, that works too. Is that within spec? Oh, that's pretty good. I think that's pretty good. 1 milliamp. Oh, look at that, bang on 1 milliamp, no worries whatsoever. Actually, that current range is out of spec. I calculated that as 0.26%. It's supposed to be 0.05% plus 5 on the 100 milliamp range. So to the 10 milliamp range, it's actually auto range that too. So yeah, slightly out of spec there, but geez, I'm not going to quibble about that straight off eBay. And using my really schmick, really expensive Wecom 10K lab reference standard, yep, it's within spec. And it's basically given the same for my little homemade reference there for 10K. Let's whack it in the 1K, see what we get. Oh, yeah! Whoa, almost the least significant digit. Yeah, a little bit under, but still within spec. And check it out, it can measure current and voltage at the same time, either voltage in the main display and current here, or vice versa, as we're doing at the moment. And you can actually see, I'm just measuring the burden voltage across the shunt resistor in this thing, and you'll see that if I take it up to 10 milliamps, the burden voltage goes up by an order of magnitude. There you go. Look at that. Oh, 1 volt burden voltage. Horrible, 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 evil. But listen to this. Tick-tock, tick-tock. They're the relays inside. It can't measure both at the same time. It's got to actually switch the relay between the two different measurements, but can certainly do it. You wouldn't want to leave that running all day, every day in some production jig, but hey, it's handy to be able to measure both. Can't calculate power though, but use a calculator or your grey thing in your head. And one of the really nice things about this meter is the serial output, as I said, but you can put it into what's called print mode. I mean, you can go into rate here and set up your baud rate and your parity and everything else, right? That's all normal. You go into second address here and you can go into print mode, and what that does is it actually outputs, this is how often it actually outputs data. We'll set this to 1 and you select auto there, and bingo, it's designed to output directly to a serial printer, or in this case, I've got a serial terminal hooked up. So here's our terminal, and look, it's just outputting text. There we go. As fast, you can actually set the rate like once per second or once per hour or whatever, and it will automatically output it in ASCII, which is fantastic. So if I plug in my resistor here we go. It's just auto ranging. There we go. That's how quick it's updating. 1K. There's our 1K resistor that I've plugged in. Fantastic. Just text. Beautiful. All this binary rubbish. So if I set that print mode to 10, then as you can see, it's happening like once per second or whatever now. So that, but that will depend on the rate. So if I go the faster mode, you can see it actually outputs, ticks over that data faster, and in slow mode it'll probably 1, 2, 3, 4, 5. There we go, every 5 seconds, and we can set that to output data at whatever rate we like. And we'll try the continuity buzzer. Oh, that, folks, is as good as it gets. Beauty. All right, so let's open this puppy up and see what we've got inside. And it'll be all through-hole tech, 1989 vintage. And, by the way, yes, we have the full reference manual for this with schematics and theory of operation and everything. I'll link that in down below. Oh, calibration void is seal broken. Well, we can, let's get rid of that, shall we? We don't care about that. Here we go. And it should just slide off, will it? Yep. No, oh, we've got some surface mount display technology. Oh, fancy pantsy. Fancy pantsy. Look at that. No battery option. We're in like Flynn, because I am presuming that the battery option goes in here. Look at that. Ah, there we go. Conductive shield may have voltages present. Have ourselves a nice big HRC fuse down there. Thank you very much. That's for the 10 amp range, of course, but it doesn't, because there's the yellow wire. That's the 10 amp range going down there. It doesn't. Is there no fuse? Oh, yes, there is. Sorry. Yeah, there it is. There's also a fuse in the holder that you can get off the front. Of course, you screw it off the front panel. So that's a fuse for the milliamp range. There you go. Just a little standard M205 there. Not a HRC type. Someone could have replaced it. I'm not sure if the original had HRC or not. And there's our 10 amp current shunt right down there. 4-terminal one, of course. It's just the nichrome like rod down there, very common, so no problems there at all. And you'll notice the isolation slot cut out. Here's our voltage input, okay, this is our main one for voltage and resistance, everything else. Nice big cutout slot in there for, looks like they got 2 separate resistors tapped off there, 2 input protection resistors, so that's very well done. But it looks like I was mostly wrong about this being through hole. It's we've got ourselves a PLCC processor. It's mostly through hole, and you can see that our separate GPIB board up here, this was the optional extra that you could plug into the thing. It says copyright 1987, so that's interesting. Yep, there it is, copyright 1987, Mr. John Fluke himself. Yeah, so that was a bit earlier. I thought it was 89. I stand corrected. All right, I've taken the GPIB board off so that we can actually have a look down in the guts here. And, well, the first thing I notice is The RS232 here, you can see it, well, the cable's coming down, sorry, you can't see it at the back, but this is the RS232 connector here. This is all the digital side of the stuff. Here's the main Hitachi processor, look at that, the EEPROM, everything else. Then we've got the opto couplers here. Nice, big, huge isolation between, and these massive opto couplers in here. That is the isolation between all the measurement capabilities. So we're going to have our Fluke ASIC under here and our ADC and everything else all under here. And that simply comes across the optocoupler, and we've got a transformer here that'd be getting power over to the other side. So power isolation transformer, you'll notice that we've got some caps on the other, filter caps on the other side there, so that'd be rectifying that and providing isolated power over here. That's why they can get away with the RS232 being connected directly to the RS232 driver there. It's all common ground for all this digital stuff, and that's completely safe because none of that goes external. It's all internal. So yeah, completely isolated transformer, optocouplers, no worries whatsoever. You'll notice that we've got a huge mains filter input cap here. We'll have a look at another angle in a sec. So this is the mains transformer coming in there. We've got ourselves just a couple of diodes in there for rectification. Filter cap. Here's the battery connector right up here. It's not populated, but that's where it plugs in. So I think that's part of that. We'll have a look at the schematic for that in a minute. And of course, spared no expense. Nippon Chemicon caps, no worries whatsoever. You'll notice that the switch is right back here on the PCB. Why is it so? You should know that I'm a big fan of those push rods and having the switches all the way back rather than run cables right to the front. That's really messy. They've put the switch right where it needs to be on these high current traces for switching in the, well, they've got to switch in between the battery and the mains transformer. So that's not a mains switch. If you have a look over here, here's our IEC mains input connector here. It's going straight into the transformer. Both wires there we go, boom, in like Flynn. And they've done the earth connection properly. You'll see that going down there. Yes, they've got a shake-proof washer down on there, but what's interesting is another earth connection here and on the other side. I'll give you a better view of this. Check it out, see? They've got another, well, it's an earth wire because it's connected to the frame of the transformer, which is connected through to the chassis, of course, which is connected to mains earth. So it's mains earth, it's going into the transformer. And as I said, there's another green wire right down there, if you can see it. That, folks, must be an internal electrostatic shield between the primary and secondary. Very, very nice. They use that in top quality isolation transformers, actually, like that one over there that I've got, that isolation transformer. It'll have a earth shield between primary and secondary to get the capacitance down between that, to get any capacitive coupling between primary and secondary. It's just a really safe way to do it. So there's no capacitive coupling, no energy can get between primary and secondary. Very, very nice. Actually, just as a little aside, if you've never seen inside one of these isolation transformers, by the way, every good lab should have one of these safety isolation transformers. Just allows you to work on equipment safely because it isolates it from the main supply, the primary and secondary. So, yeah, fantastic. Tortec, Australian manufacturer of these things, they've been making them for decades. They're one of the leaders in the business. And this one, it's a huge toroidal transformer one, awesome, but you'll notice it's also got the electrostatic shield in it. Here we go. We've got that, the input mains earth goes down to here, of course, and then you can actually see it coming off here, and you might be, there we go, you can see it. Anyway, it's going into the base of it, it's going inside the transformer because they've got an electrostatic shield, it's called, inside between the primary and the secondary. So that basically cuts the capacitance completely down to zero. So there's no coupling between the primary and secondary. So common mode noise actually stays on, it can't get through from the primary side over to the secondary. So that's going to be, that internal electrostatic shield is going to be closely coupled to the primary side. So Fluke are doing exactly the same thing inside this transformer to get that common mode noise down. Very nice. Check it out, folks. State-of-the-art processing power. The Hitachi HD6303. This is a 6800 series compatible. It's sort of like a later variant of the 6800, backward compatible. It's got a built-in serial communications interface. Fantastic. So hence it can drive the RS232 directly up here within the chip. Oh, fantastic modern technology. I just love it. And of course, none of this E-squared prom rubbish inside, so we got ourselves a separate National Semi 63 C46 down there to hold, presumably, the cow values. And we've got a shielding plate on the bottom, so we'll whip that off. And as you saw, we had a conductive shielded box on the top side. And it's mostly shield on here, but what you really notice are the guard rings. Check them out. Explained guard rings before. There we go. Crisscrossing in there, designed to stop leakage between individual nodes in here. So they obviously don't care about leakage between these two nodes, i.e. if you're getting any contaminant or condensation on the board between those two terminals, doesn't matter. But it certainly matters if it's between that one and that one there. So they put a guard ring around that, and that's kept to a common circuit level, and they're all connected back to that common via down there. So that would be a ground reference guard point in as part of the analog to digital converter circuit. And by the way, we have a date code on this puppy. There we go, first week 93 for that chip there. So yeah, we're talking probably early to mid 93 construction. We've well and truly lifted the skirt on all the ADC front end section, so let's take a look at it. As I said, here's the main voltage input here, and here's our two input protection resistors here. What are these funny looking things? There's a cutout slot underneath that, if you can see it. There we go, you can just see the slot. Those are going to be surface mount MOVs. Let's go to the schematic. So here's our four front panel terminals here. Here's our common. Here's our 10 amp input, of course. There's our big HRC fuse going straight into the current shunt. Bob's your uncle. That's all fairly typical. 4 terminal tapped off that. Of course, you've got to tap the ground off this side of it, not from that side. So you've got to tap from the signal side. Anyway, that gives us our 10 amp input here. Here is our milliamp fused input, so that's showing that the fuse is in the holder on the front. Looks like we do. Do we have another internal fuse? Oh, I must have missed that. Anyway, that is going through our current shunt resistor for our milliamp range. I can show you that in a second. And bingo, here's our MOVs here, which go down to signal ground, and here's our positive inputs here. So our positive input goes across here. Here's one of our resistors, R5 and R6 here. These are our two resistors that we saw across that isolation slot. And bingo, we've got effectively then two MOVs in series going down to ground at that point. Now, other MOV here is connected on this side of the other big input resistor across the slot there through a PTC here, so providing some overcurrent protection there. Actually, the real board is slightly different to the schematic. You can see R5 here comes across, goes into one of our MOVs here, okay, which is the other common side to this over here, but then it also goes into the high voltage input divider here, one of our thin film ceramic hybrids, one of 3 on this thing, and there's our PTC there. So what's going, yeah, it's actually different to the schematic. Yeah, substantially different, and this shows 3 MOVs here, and we've only got 2 down in here, so yeah, it's a slightly different configuration, might have a version difference here. Anyway, past our input protection there, however it happens, they go through the relay contacts for the various ranges, nicely annotated there, so you can figure out those for those playing along at home. You'll notice that all these resistors here labelled Z1, that is because they are part of the input precision thin film resistor network in there. Very common, high stability. The reason they build them on the ceramic bases, they're incredibly stable. They still do that today, of course, and this puppy has no less than 3 of them. Very nice. Basically what that translates to is you're going to get very little drift over the years. They're going to be super high quality, super low drift, super precision, and they're going to be matched as well. So it's very likely that if this thing is in calibration on your 1 volt range, it's going to be in calibration on your 10 volt range, for example. And if you're wondering where that guard ring on the PCB was connected to, there we go. It's labeled guard. Fantastic. I know what you're saying. Show us the reference, son. Well, all right, here it is, VR1. There we go. It's just a Xeno diode. Well, when I say just a Xeno diode, it's selected with a wise old man with a grey beard as he strokes it. Well, okay, maybe not that good in this class of instrument, but hey, the production test jig that actually measured and characterized these things and selected them would have been set up by a guy with a grey beard. And here's the main output from our analog processor chip. This is a custom Fluke ASIC. Of course, they rolled their own ASICs. They still do, I think. So, yeah. And once again, there's those big opto couplers we saw going over. So it's just the serial comms data coming directly out of the AD converter itself. And for those playing along at home, there's inside the big custom Fluke analog processor. It's got multiplexers and switches and all sorts of things. It's got the voltage reference for the ohm source and everything you could possibly need to roll your own front-end converter. And you can see our input signal here being AC coupled off here, goes through some relays up to a AC buffer up here, and then here is our true RMS converter. It's off on a second board, which I'll show you, and they've got a separate schematic for that. So there you go, there's the RMS output there, so they can actually feed that in. So yeah, that's pretty convoluted. Jeez. Warning, Will Robertson, warning! We have dipped tag tantalums, look at them! Oh, evil, evil. But there we go, classic. What else do you find in a true RMS converter in a multimeter? Analog devices, AD637. Yawn. So why would they actually have that on a separate board? Why not? It's not like a paid option. Why not just whack it down on the main board? Well, they could have squeezed it in. It's probably not a space issue there, but my guess would be that maybe they secretly do offer a non-true RMS version, just an average responding version. That's quite common for the military market, actually, because they've got all their test procedures and everything for, use a multimeter on a boat or whatever. They've got all these test procedures written for how to test stuff using an average responding multimeter. And you can't have any of this newfangled true RMS rubbish. No, they'd have to go rewrite all their manuals, all their test manuals. So they will order specific non-true RMS average responding versions of various Fluke meters. That's actually quite common. And those 0.12 MFD caps look pretty special. MFD, of course, is microfarad. None of this nanofarads rubbish. No, sorry, Bob. Back in the day, capacitors came in microfarads and picofarads, puff, and that was it. So if you wanted a 1 nanofarad cap, it was 0.001 microfarads. Thank you very much. Anyway, the reason that looks special is because that's probably some sort of high stability, even though it's plus minus 10%. The absolute tolerance doesn't matter. It's a very temperature stable cap. This is part of the active filter circuitry, and it needs to be stable, so they've probably got a polystyrene, put the kettle on capacitor in there. And of course it would be end of life as we know it for the volt nuts if I didn't show the reference diode. And there it is, just sitting there, not getting into it, not getting out of it. Well, it's Bass straight or something.
I look in the corner and there's Bass sitting there, not getting into it, not getting out of it. I said, what, is Bass straight or something? Boomer said, as a matter of fact, mate, he's a cop. I said, you're joking, mate, a cop? I'm getting out of here, let's go, Anna. She said, no way, I'm hanging around all gum leaves.
Well, there's the main Fluke analog processor, and well, it's about all she wrote. So here's the power supply schematic for you power supply aficionados, and let's have a quick squiz at it. Here's our mains input transformer. As we saw, there we go, there's the internal electrostatic shield. You can see it going down to the earth there. And as I said, this thing is always on. Here is the actual on-off switch after the full wave rectifier here. So as you can see in the off mode, it can actually come in from the battery here. The battery board connects up to there, and we don't have that battery board, so we won't bother looking at the circuit for that. But as you can see, the LM3578 here, with our transformer here and our output diode here, there we go, that's forming the plus 5 volt, the main logic supply voltage. And you'll see that actually it's a really weird arrangement how they've drawn it. It's just like, you know, it's not very typical, so it's not obvious at first glance. But here's our output diode, and here via our output resistors here we go, they're our current are they current sense resistors? I think they might be tapping it off there for current limiting. It goes out here, bingo, there's our plus 5 volt rail. And that 5 volt output after the current sense resistors, it's then powering this oscillator here for the primary side of this switch-in converter here. And this is another convoluted arrangement that gives us plus 5 volt, plus 5.2. I'm not sure why they need 5.2. Anyway, 5 volts AC, minus 30 volts, minus 5 volts, and yeah, a few rails to make this puppy work. And then we have our vacuum fluorescent display board and all the switches as well. There, vacuum fluorescent display driver, that's the UPD 7512 or 75212. I'll try and link in a data sheet. Actually, that is different again. It's a UPD 7527A. This is actually a 4-bit micro, believe it or not. Actually, that front panel display board, look, copyright 1996. Does anyone know the exact date they released the Fluke 45? Leave it in the comments. And by the way, the manual says this thing used an 8-volt rechargeable battery pack. It's rather bizarre. Here's a photo of it. And what's the standby power consumption with the switch off? Well, just over 1 watt. That's all right with just the transformer and the output rectifier and filter caps energized. And we're looking at 8 VA. And the power factor is awful, as you'd expect. So I hope you enjoyed that look at this venerable Fluke 45, the world's first dual display multimeter from the late 1980s. An absolutely classic meter that still holds its own today spec-wise. So if you can pick one up in good condition at a reasonable price, do yourself a favour and get one, because they're a really nice little bench meter. I like them. So even though the Fluke 45 seems to be one of the forgotten meters of the era, or one of the forgotten Fluke meters, it still seems to hold quite a bit of premium on eBay. So, you know, you might have to be patient to pick one of these puppies up, but, you know, if you can, by all means, do it. And as always with my teardowns, I'll have some high-res photos I take as I disassemble the thing. They'll be on my EEVblog.com website, so check the link down below. And as always, you know, thumbs up, and yeah, not a fake thumbs up, please, from paid bots. Real thumbs up only in that direction. Thanks. Catch you next time.